So let's continue solving systems of equations. All right, take a look at number 5. You can see that in number 5, these are linear equations. It's just that top equation, nobody likes to work with fractions. All right, to avoid the use of fractions, let's get rid of all these fractions. Let's get rid of the 1/5 and the 1/2. 5 and 2 both divide into 10. So let's multiply everything in this top equation by 10. All right, so I'm going to come down here and record the new equation that I get as a result of multiplying every term by 10. If you want to think of 10 being a fraction and 10 over 1, that might help you do the computations. Well, I know 5 will divide into 10 2 times. So the 5 divides out, leaving me 2 on top. Well, I have to multiply the 2 by the 1 that's there, and I keep the x. So 10 times 1/5 is 2, keep the x, plus 10 times 1/2 is 5, keep the y. And don't forget to multiply 10 by 8, so you're going to get 80. All right, this is a little more friendly. And then I'm just going to go ahead and record the second equation. So we're solving by the method of substitution. You want to identify any variable term that has a coefficient of 1, and in the bottom equation both x and y have that coefficient of 1, so it's really your choice. Do you want to solve it for x equals, or do you want to solve it for y equals? And to mix things up, I'm just going to solve the bottom equation for x equals. Meaning I need to subtract a y, so x equals 20 minus y. So looking at the top equation, wherever I see x, I'm going to replace it with 20 minus y. All right, so come down here. Let's kind of make a little, separation of my work as I change, thoughts or concepts here. Not concepts, but just thoughts. Kind of change our work here. So 2 times x needs to be replaced with 20 minus y. Record the plus 5y and equals 80. Distribute the 2 in. Let's collect. So I'm going to have 40 plus 3y equals 80. Subtract a 40. Divide both sides by 3. I'm going to leave my answer as an improper fraction. It's simplified, so I'm just going to leave it as 40/3. All right, so let's get the x that belongs to this y. So I'm going to come back up here to get x. I'm going to insert 40/3 for this y. So x equals 20 minus 40/3. All right, let's go ahead and jump in and get a common denominator. All right, well, first of all, I'll rewrite 20 as a fraction, 20 over 1. You're going to multiply the top and the bottom by 3. So x equals 60/3, which makes sense. That is 20 minus 40/3. So x is 20/3. Not as bad as what it first might have looked like it was going to be. All right, moving on to number 6. Noticeably, what's different is that the bottom equation is not a linear equation. It's a cubic equation. So thinking about what a cube graph looks like, the general shape of a cube graph would be something like this. Okay, and if you were to intersect that with a line, it's very likely, it's going to happen that your line and your cubic should have some points of intersection. So I have no idea what these look like, but I don't think we're going to be able to avoid having a solution. And it's quite possible that we have multiple solutions. In the linear systems, all the previous 5 examples, we only had one point of intersection with those 2 lines. But now, because we don't have both linear equations, we could have multiple solutions. Technique's still the same, method of substitution. I think I'm going to take the top equation, because y has a coefficient of 1, I'm going to isolate y. So in the bottom equation where I see y, I will replace that with negative 3x plus 2. Where y is, I'm going to have negative 3x plus 2. I should have just made that a subtraction. Then go back and it's supposed to equal 0. Well, conveniently, your 2's will cancel. It's a good thing, because if I'm supposed to solve this algebraically, I wouldn't have been able to factor had those constants not zeroed out. But now let's take out the common factor of x. Let's set each factor equal to 0. Notice I'm going to get multiple x coordinates. Remember, when we bring in the square root, bring it in on both sides. If you have an even power, 2, 4, 6, 8, 10, we take out the absolute value. Not for odd powers, even powers. And when you remove the absolute value, make that positive negative adjustment. So in fact, we have 3x coordinates of points of intersection. So this cubic, whatever it looks like, and this line have to intersect in 3 different points. We're not done. We've got to get the y's that belong to these 3 different x's. So one at a time, we're going to take 0, positive square root of 3, and negative square root of 3, and I'm going to get the y's by replacing those 3x values into this equation right here. All right, so when x is 0, I'm just trying to keep it all organized here. Well, that's going to be negative 3 times 0, which is just 0 plus 2, so y is 2. So 0, 2 is a solution. All right, now let's see what y belongs to positive square root of 3. So I'm going back to the y equation. Y equals negative 3 times square root of 3 plus 2. All right. All right, so the solution here is when x is square root of 3, y is going to be negative 3 radical 3 plus 2. Unless you need to, don't change that to a decimal. Just leave your answer exact. All right, so those are 2 ordered pairs of intersections. Let's get the third one. All right, going back and looking at what y was, it's going to be negative 3 times negative radical 3, so that's going to be a positive 3 radical 3. And the rest of that y equation is plus 2. So the x was negative radical 3, and the y that belongs to that is 3 radical 3 plus 2. You might want to take a look at what that looks like on your graphing calculator. Maybe solve them both for y. This equation is already solved for y. Put it into y1. Solve this equation for y. And then visually see the 3 points of intersection. All right, 2 more. Notice that in these last 2 examples, we have a linear function intersecting, possibly intersecting a quadratic. So let's just see what happens. All right, let's solve this by the method of substitution. All right, so my approach in 7 and 8 may look a little different. We could have taken this approach in number 6 too, just so you're aware. Okay, top equation has a coefficient of negative 1 for y and for x. Bottom equation has a coefficient of 1 for y. My thinking is I'm going to go ahead and solve both the equations for y and then set those 2 equations equal to each other. So for the top equation, I'm going to add the 2 to the x side. And then I'm going to add a y to both sides. Bottom equation, let's get y by itself. Y equals 8 minus x squared plus 2x. All right, so method of substitution. Look, both equations were solved for y equals. This is still the method of substitution. So what I'm going to do is, because both of these are y equals, I'm going to set x plus 2 equal to 8 minus x squared plus 2x. It's quadratic. I want to zero one side out. What makes the most sense to me is add x squared to the left side so that it becomes positive. So I have x squared. You're going to subtract a 2x with this x, so that becomes minus x. I'll subtract an 8 to the 2, so that's minus 6. Okay, we have a quadratic equation. You can try and factor it. Quadratic formula works on everything, though. But I do see that this is easily factorable. All right, set each factor equal to 0. So this linear factor produces a solution or root of 0 of x equals 3, and we have x equals negative 2. All right, so these are both x's. They both need their own y's. So let's go back and one at a time find the y's that belong to these x's. So when x is 3, I'm going to choose this equation right here. I'll trade sides. Y equals x, or 3 plus 2. So y equals 5. All right, now when x is negative 2, y equals, when x is negative 2, I'm going to have negative 2 plus 2, or 0. All right, so my other solution will be negative 2 comma 0. You can check your solutions by typing each of these equations into y equals lines and locating the points of intersection, and it should be that you get these two ordered pairs. All right, let's take a look at number 8. All right, same technique. I'm going to solve both equations for y since they have a coefficient of 1. So I'll add a y to the right side, but I need to bring the 1 to the left side. So the result would be 2x squared minus y, 1 equals y. Likewise down here, I'm going to add a y to the right side, but subtract the 2 to the left side. All right, these equations are equal. I can substitute x minus 2 in for that y. Same thing as just setting both equations equal to each other since they're both equal to y. We have a quadratic equation. Let's zero out one side. The right side makes the most sense because my x squared term is already positive. So I'm going to subtract an x, and I'll squeeze it in here. I'm going to add a 2 to the current negative 1. I think that was a minus. Add a 2 to the current negative 1, so that's plus 1. All right, just trust me here. I tried to factor it. It's not factorable, so I'm going to have to go to the quadratic formula, see if I can get some x coordinates. It doesn't sound like it's going to look real pretty, but let's see what happens. Quadratic formula. A is 2, B is negative 1, and C is positive 1. So opposite B. Oh, my goodness. Minus 4 times A, 2 times C, 1. All over 2 times A. 2 times 2 is 4. All right, 1 minus 8. We have imaginary solutions. That's a circle with a line through it. No solution. So you just record no solution. It means there's no point of intersection. If you were to graph both these equations, y1, y2, you would see that this parabola and this line don't ever intersect. Perhaps it looks something like this. All right, so that's solving systems of equations by the substitution method. Not always linear systems, but sometimes could be a quadratic system or cubic system or a combination. Sometimes we have answers, intersection points, and sometimes we don't, but the math will determine that for us.